cloud glaciation. And basically, I will go from the very small scale, from droplet freezing, to the biggest scale of climatology, where we can start talking about cloud phase seasonality. So to start, why do we want to study cloud glaciation? So we did have some 1,000 years ago so-called rain-making shamans that used to tell you, if you light up a fire and start dancing around it, then you will eventually call the gods of rain and make clouds rain. So this was kind of aerosol cloud interactions at the time. And people believe that, right? So now we believe we have a much better theory of why clouds precipitate. And we did discover in between aerosols and ice nucleating particles, and we do now believe that these ice nucleating particles have a lot to do with rain formation. Because cloud droplets, once they get in contact with these kind of particles, temperatures between 0 and -35 degrees, they will form ice. And this ice will grow quickly and fall down from clouds and eventually form rain. So the revised version nowadays is that it's not dancing, right? But aerosol was playing an important role in rain formation, at least in mixed phase clouds. Another reason why we want to study cloud glaciation is because we're interested in climate projections, and we know there's a really wide spread in the estimates of equilibrium climate sensitivity between the last generation of models and the new generation of models. So in this figure of the IPCC, we can just see the wide spread in between models. And it is believed that the change in the new generation of models, where we have a higher climate sensitivity, may be because of the negative phase feedback, which is strongly associated with cloud glaciation. So basically, to understand this cloud phase feedback, we have to focus on mixed phase clouds. So between 0 and -35 clouds, we can have liquid or ice. And in the case that we have a high ice frequency, then in a warmer climate, the clouds that will be converted from ice to liquid will be rather the lower clouds, which have a higher optical depth. So we will have a strong increase in the cloud reflectivity. But now if you think of the new generation of models where you have a rather lower ice frequency, then in a warmer climate, the clouds that will be converted from ice to liquid will be rather the thinner clouds that you have higher up in the atmosphere, just because of how humidity is distributed on the atmosphere. So as a result, we will have a much weaker cloud phase feedback, which will be traduced into a much higher equilibrium climate sensitivity. So this is the second important reason why we want to understand cloud glaciation, because it will control how much ice we find in this mixed phase regime. Now the difficulty of studying cloud glaciation is that it's a really multi-scale process. And on this figure here, I have extended all the different objects that you can focus when studying cloud glaciation. So you really start from the scales of water vapor and aerosols about nanometer scale, and then you can trace the effects of cloud glaciation also looking at the entire planet. So if you sum up all these scales, and we're talking about something like 15 orders of magnitude on the spatial scale, and for each of these objects, we have different fields studying the processes. So we have chemistry studying the composition of aerosols that can trigger ice nucleation, and we end up at climatology, where we try to see patterns of ice frequency on the whole planet. And in between with this box, we have the mesoscale, where we have difficulties recognizing patterns because everything is kind of fuzzy when you go from ice and droplets up to the point when you find again a cloud, which is kind of nice to see and recognize. So this is important to remember for the talk, that this mesoscale is rather complicated. Now, how do we research cloud glaciation? So basically, the approach is the same that you follow in every field of physics, which is reductionism. So you start from the smallest part of your system, and then you try to study the rest as an emerging property of the smallest scale. In the case of cloud glaciation, this would be droplet freezing in ice crystals that we try to understand very well, so that we put it on our models, and then we can simulate clouds right, and then hopefully also understand what's happening on the global scale. So now I want to go also into the process that are important for cloud glaciation at every scale. So on the smallest scale and the micro scale, we have droplet freezing. So basically, we understand how aerosols can lead droplets to freeze. There's been a lot of efforts in the last decade to really quantify the efficiency of different aerosols. So even though this is improving for the global perspective, I have to say, and for me, this understanding is quite good right now. But if we move up into the scale, we start encountering some problems, and that's because when ice forms, ice is much better at joining water vapor molecules compared to droplets. So they will really quickly grow into different crystal habits depending on humidity and temperature, and this will really dominate the ice to liquid balance in a cloud. And to exemplify why this process is so important, the so-called depositional growth or Berger-Sanfinaisen process, we can take a look at this picture more closely. So here we have an ice crystal surrounded by cloud droplets. And if you start counting droplets, then you realize this ice crystal has grown by depleting something around 1,000 droplets. And if you think it all started with a simple ice nuclei, then you realize how big is the leverage that these particles can have if they trigger this depositional growth. And this process is not that well understood, and this is one main point of uncertainty when we try to simulate this cloud glaciation in models. When we go higher up into the scale, then we encounter different processes that are also problematic, mainly controlling the development of the ice crystal number. So most of the models have an aggregation processes controlling how these ice particles will aggregate with each other and decrease the crystal number. But from many observations, we know that basically a lot of often what it happens is that ice multiplication processes kind of produce more ice crystal numbers compared to the number of ice nucleating particles that we see. So there will be a lot of competing processes controlling the number of ice, and sometimes we find several orders of magnitude difference between the ice crystal number and the ones that we expect. So I would say in this regard, we have a rather poor understanding. Now, if we move into the mesoscale, after some minutes to hours, then whether a liquid cloud will glaciate or not will depend on another on many other factors, such as, for example, how sedimentation is working on the model that you're using. So in case we have, for example, quick sedimentation, then at some point we will get all the ice produced out of the cloud, and we will stay with a liquid cloud. But if this sedimentation is more slowly and we have a continuous production of ice crystal, then we can end up with a more stable mixed phase cloud, which will be here the second example, which will be continuously producing ice, and we could encounter then regions in this cloud where we have both phases happening simultaneously. And if the ice crystal number is enough and its sediment is low enough for it to really gather all the water vapor out of the liquid cloud top, then we eventually could be able to see a glaciated cloud after the cloud top kind of gets depleted. And this part here, which conditions lead to which kind of development of a mixed phase cloud, is also rather poorly understood, and hopefully will improve with the next generation of models, which are trying to reproduce this with higher resolutions and better parameterizations, but it's still a work in progress. And now the problem is that we have gathered a lot of uncertainty up to the mesoscale, and now I will start talking about the global scale. So the important thing is to also mention through this shift from the mesoscale of the global scale, we will have a lot of questions already that we have to solve. And now in models, when we try to look at the mixed phase regime and all these different processes, we will have also different approaches that we can follow. So we can basically use cloud resulting simulations, which have a resolution capable of reproducing kind of the some of the turbulence of these clouds. Then we will encounter some other type of models that we can use, so-called large eddy simulations that go really fine to the scale to try to also get more and more of these small eddies that we have on a cloud. Or we can use, as I do, global climate simulations, which kind of have to parameterize, simplify much of this process in order to get mixed phase to work over the whole globe with a efficiency that allows us to simulate several years. And now if we go to the global scale, we have, of course, a lot of influences from atmospheric dynamics. So we will have different fronts and different relative humidities in the environment and different updrafts that will, of course, affect how clouds develop once they get into the mixed phase. And lastly, if we get everything right, then we can start doing some climatological statistics on mixed phase clouds, which is basically try to separate clouds as we observe them from space into glaciated clouds and liquid clouds, and try to see if we find patterns that we can relate to some of the processes that I just mentioned in the last slides. So this is basically the scales where I work in. And to explain a little bit what we can do here is sometimes we will have liquid clouds that will start producing ice and then eventually get to a glaciated state. And this can be observed from satellites because we see cloud tops, and then eventually we will count more ice cloud tops at a certain temperature, and then we hope that this is a result of this cloud glaciation. But the problem is that there are a lot of other processes going on in this mixed phase regime. And sometimes we will have some confounding effects from, for example, cirrus clouds that can sediment down into warmer temperatures. and of course the cirrus clouds are not started from droplet freezing, but from other processes, and this can make this kind of climatologies more difficult. And for warmer temperatures, sometimes they are more affected from whatever happens above them, for example, through feeder effects of ice that's being produced at colder temperatures. So it's not always easy to use climatologies to study cloud glaciation, but normally you assume that whatever is happening with the frequency with the ice to liquid frequency of cloud tops is at least partially related to this cloud glaciation. But of course, this has to be improved, and this will be something that I will also talk about towards the end of the talk. So now that we have kind of the whole picture, I want to talk about some results that I have gathered mostly from satellites and mostly from global climate models during the last years. So basically, you can do modeling and observation at the microscale, mesoscale, or macro scale. I would say most of the efforts are concentrated into the mesoscale, doing campaigns and using weather simulations. But I focus on the right side of this diagram, and actually I start from the top right, which are satellites. So the idea is to start here because most of the effort is being done from the left to the right, starting from laboratory experiments. So I thought it's a good idea to start from the other side of the equation. So to try to study droplet freezing using satellites. And for this, I use some pretty interesting patterns that you find in the atmosphere. So mainly that dust, which is a really good ice nucleating particle, occurs mostly on the northern hemisphere, and also during spring. So if you take the whole constellation of clouds, there are some clouds in the mid-latitudes that fall into the mixed phase regime, and also overlaps with the regions where you have dust coming from the Sahara, from the Dust Belt, and you can both do an hemispheric contrast and a seasonal contrast to try to find correlations between this cloud glaciation and this INP variability. So concentrating on these clouds on the mid-latitudes and on its correlation with dust emissions, in this natural laboratory, what I started doing was to try to define regions and temperatures. So here, temperature in the y-axis and latitude on the x-axis, where we find the highest contrast of the cloud ice to liquid frequency. So the regions that I'm showing here is where we have much more ice clouds at the same temperature compared to the southern hemisphere. And the different colors are different cloud products because different satellites are really different, are very different at identifying these ice clouds. But we do see a pattern, and we do find that most of the different satellite products, which are the different colors here, show a very high contrast between hemispheres at the mid-latitudes, somewhere between 40 and 70 degrees north or south, and at temperatures about -30 degrees, which actually happens to be the temperature where ice nucleating particles from mineral dust are believed to be very efficient. So then we check the regions where we have a really high difference in dust between the northern and the southern hemisphere, and we find a really nice overlap, which is mostly because the Southern Ocean is so pristine in the mid to high latitudes. And the highest overlaps, of course, at these temperatures where we think that dust ice nuclei are really efficient. So this is kind of an argument towards believing that dust may be somewhat controlling these patterns in the cloud ice to liquid frequency. And now we can repeat this for the seasonality of this ice frequency, and we find similar patterns. So again, we have a strong spring to fall difference because in spring we have the highest dust emissions in both hemispheres, and we find a strong correlation in the northern hemisphere in those regions where the spring to fall difference in dust is the highest. We also find a pretty high difference in the ice to liquid frequency. So in this case, inside each region is we find a difference of at least 10% higher ice frequency during spring. So this shows this correlation between dust and ice frequency, both spatially and temporally because of the seasonality. And then the next step was to prove that this may be coming from the microscale, from the droplet freezing, just interacting with these ice nucleating particles. So for the next study that I did during my PhDs, I tried to lean over to the simulations and try to see how climate models could reproduce these patterns that I found from satellites. And the first experiment was to try different droplet freezing schemes, which are the different colors here in this plot, and checked how the mid-latitudes, how the cloud ice frequency at the mid-latitudes change at different temperatures. And the most important line here is the black line, which is the case where we shut down droplet freezing completely. And the high line here, the blue line, is the observations. So we can already tell a lot from the simulation without droplet freezing. And this is that even without droplet freezing, we have a lot of ice, which is coming from the lower temperatures. So kind of zeros that either sediment down into the mixed phase or just advect to warmer temperatures, at least using this model. And then for every different scheme of droplet freezing, we find higher frequencies of ice, which will be due to this cloud glaciation because of this dust IMP. So in these schemes, we only use dust as an IMP. But we are more interested into replicating the patterns, the difference between hemispheres and seasons. So moving from the mean state, we looked at how the contrast changes for different schemes. So here again, the black line is the more important line that shows that at all temperatures, we do not find a significant difference between hemispheres in terms of the cloud ice frequency when we shut down droplet freezing. But we start to see a contrast when we turn it on. In the case of the red line was the default scheme for droplet freezing. And we find out that we had to tune the droplet freezing rates by about 3 to 4 orders of magnitude before coming anywhere close to the satellite's observations. And reason for this, so the case of the enhancement will be the yellow line here. I think one of the reasons has to be either ice multiplication or Bergenson phenizing process, but I'm still trying to decipher this. And then, of course, this is only the hemispheric contrast. So what about the seasonal contrast? So we reproduced this again for the seasonality. And we find out we find actually something pretty similar. Without droplet freezing, you cannot replicate this this seasonality that we find in satellites that we can see on this background area, this cyan line. But different schemes can eventually reproduce the droplet freezing in a way that we also find this seasonality in the cloud ice frequency. So we are doing a high spread here, which is to try to explain a global pattern using different schemes of a microscale process. But again, it shows that even doing this high spread, droplet freezing from mineral dust appears to be quite important for these global patterns of the cloud ice frequency. And because this was so so impressive, I now tried to move a bit more into the seasonality of cloud ice frequency, try to lean over from the global averages and mid-latitudes, try to move into finer resolutions of these patterns. So basically, I started using active retrievals of satellites, and now I use passive retrievals just because they have a much higher temporal coverage. So what I'm doing right now is basically I take a 2x2 degrees grid box with different clouds, with different cloud temperatures, and try to bin them over temperature to try to find simple statistics of what is happening worldwide. So in this case, just separating clouds by its cloud temperature, and then we can repeat it for cloud phase and for other cloud properties. So because we have so much data, 35 years, then we can really repeat this and bin different properties like cloud phase and optical thickness. And we can start averaging these properties. For example, cloud phase is a binary decision normally between ice and liquid as detected from a satellite. But once you gather enough data and move from daily average to seasonal average over 35 years, then you start to find normal distributions of this cloud ice frequency. To the point where you can do really point-by-point comparisons with a resolution of 2 degrees. But the catch is normally you have to count up for clouds being too thin or too small because they will suffer from biases from whatever is happening below the cloud. So we try to get rid of effects from cloud corners and thin clouds by just taking the optical thickness, of course, and the cloud volume fraction. So basically, we take only clouds that are really thick and clouds that are pretty stratiform, so that are pretty extended within a certain temperature level. This is about 10% of the data, but because we have 35 years of data, we still have enough. So if we now repeat this seasonal contrast, so how much ice do I have in spring against how much do I have in fall over the whole globe using this data, we can start going really fine and see where this seasonality is happening. So in this map, for example, I plotted the difference between spring and fall in terms of the cloud ice frequency. So blue values means more ice in spring, and everything at a cloud top temperature of about minus 20 degrees. So the first thing that we see is a pretty nice agreement with our past study. So we see more blue values, so more positive correlations in the northern hemisphere compared to the southern hemisphere, at least in the mid-latitudes. But these maps, of course, starts new questions like what is happening on the poles and what is happening in the subtropics. And this is what I'm trying to explain now. And eventually you have to go back to the climate models and try to test different hypotheses that can explain why I am seeing this map of different seasonalities at different regions of the globe. And the second problem is that we not only have mixed phase clouds, so liquid clouds that just get glaciated, but we can also be having some noise from cirrus clouds going into the mixed phase regime, which is what I believe it's happening on the subtropics. So it's becoming pretty interesting to check these patterns of seasonality around the globe. You can also start looking at winter, summer differences, so not only spring, fall differences, and try to explain why we see some patterns correlating pretty closely to the double intertropical convergence zone. So this is a work that I just started, but hopefully looking at the seasonality at such a fine scale can push the climate models to try to find out more about what's happening on the micro scale and to try to understand cloud glaciation more. So up to now, there's a lot to explain, I believe, and I'm really looking forward to start the next phase of global modeling to try to answer some questions of how, for example, sea ice variability may be controlling this seasonality that we see, and how isotherms, height, for example, may play a role. And if you have any idea of why these patterns are sometimes so strongly, for example, in the polar oceans, then please let me know at the end of the talk. So that's kind of the last study that I wanted to present, and I just want to let you to spend some seconds on these maps in case you come up with an idea. And now I just want to conclude about why I think everything, all that I show is important. And it's basically by using a top-down approach instead of the traditional bottom-up approach, we are much closer to the scales of cloud glaciation. And I believe that there's a really nice synergy between satellites observation and climate models that can lead to new understanding of what's happening inside clouds and even at small scales of microphysics. So I will keep going that way, I believe, for the next years. And I think I will focus on trying to get the temporality of cloud glaciation right. So to try to understand how long does this process takes, and really to try to pin down exactly where and when clouds glaciate, and well, like I said, how long it takes, and try to filter out clouds that may be confounding in the relationship between cloud ice frequency and droplet freezing, like I mentioned, these cirrus clouds that may get into this mixed phase regime. And I think eventually you have to start doing cloud tracking for this. Otherwise, you can never be sure that the cloud that you see, the ice clouds that you see are really coming from the process that you are studying, that you want to study. So at this point, I will be very happy to answer any questions that you may have.
Okay, well, great, Diego. Thank you for that very interesting talk and a bit of a different approach using the top-down approach to cloud glaciation rather than some of the microphysics studies that a number of us do in ICCP. So it's a great contrast. So at this time, I'd like to open the floor up for any questions or comments that people may have for Diego.